started talking about the 3-qubit code. So let me remind you, the idea was that we had these three logical states, 0 tilde, 1 tilde, and 2 tilde, which we represented. We argued that there was a way of representing them where you take the unencoded 0, 1, or 2 and put it on the first of the physical qubits, and then we put this maximally entangled state chi on the second 2 qubits, and then I claimed, and you were supposed to check, that there was a unitary transformation with support only on the first 2 qubits that turned this state into the encoded states that I wrote down yesterday. And this chi was this just this maximally entangled state. And then moreover, we argued that this structure allowed us to recover any quantum information in the code using, manifestly using only the first 2 of the qubits, and then using the symmetry of the code that we could also similarly decompose the state in the same way, with this being 1 and 3 and 2 and 3. So we saw that the state any encoded state could be recovered on any 2 of the qubits. We also saw that if you have an operator, O tilde, which is called a logical operator. So by the way, the subspace spanned by these 3 states is called the code subspace. It's a 3-dimensional subspace of the Hilbert space of the 3 qubits. So we also defined logical operators to be operators that act within the code subspace, so that with some matrix elements OJI, and we asked also the same for their Hermitian conjugates. And then we saw that actually any logical operator also could be represented on any 2 of the physical qubits. Because, for example, if we want to represent it on the first 2 of the qubits, then we can act with U12 dagger to remove this. And then while the logical information is just sitting here on the first qubit, we can just act with these matrix elements on the first qubit, and then we can re-encode to get back to this. And that gives us an operator with support only on the first 2 that acts in this way on the code subspace. And we can do that for any operator on the code subspace. So now I want to explain why I think it's reasonable to view this as a model of holography. So let's say what the map is. So there's a picture, which I'll draw here. So this will be like a time slice of the bulk. And then let me put 1, 2, and 3 here. And I'll put a dot here. And then let me write the words here. So the idea is that the 3 physical qubits are the boundary CFT. And the 1 logical qubit is bulk effective field theory. Okay? And so that's what this picture is showing, is that you can think of, so the boundary CFT, it's a local theory. So there's, here it's a lattice theory, and it's a very primitive lattice theory. It has 3 lattice sites, and here they are. Here, here, and here. Those are the physical qubits. The logical qubit, so the idea is now the bulk theory is also a lattice theory, and it's even more primitive lattice theory. It has only 1 lattice site, and it's sitting right here in the center of the bulk. So then we can draw these Rindler wedges for the 3 boundary regions. And what this discussion here shows is that indeed any logical operator, so now these logical operators, you should think of them as being like, phi and phi dot of the bulk field sitting here at the lattice site and everything that's generated by those. So we saw that phi and phi dot in the center of the bulk could be represented on any two of these boundary subregions. And that's exactly the structure that we got out of the AdS Rindler reconstruction. And moreover, we can also show, so we had this puzzle about, how can the thing in the center commute with everything on the boundary? Well, here we can look at that here in this model. So say that psi tilde and phi tilde are states in the code subspace. So, just some superposition of these three states. We can look at the commutator of any logical operator, which is a field sitting here in the center of the bulk, with an arbitrary boundary operator, say, that's localized on the third Q-trit. Okay? So an operator that acts with support only on one of the physical Q-trits is like a local operator in the boundary CFT. All right? But now let's look at this. Well, this operator O tilde is always acting either to the left or to the right on a state that's in the code subspace in this commutator. And so here's why it's important that I wrote the equation both with the dagger and not with the dagger. So that means actually in this expression I can just replace it by O12 without changing anything. But now these guys have support on different Q-trits, so this commutator is 0. And had I put x1 here or x2 there, right, then I would have just chosen the other, the other u, and I would have still managed to arrange for it to commute. So we see that at least in matrix elements within the code subspace, I can have non-trivial operators that commute with all the local operators on the boundary, which is basically the sort of the hallmark of radial locality, right? And so, and so in AdS CFT, right, like the sort of zeroth order weird thing is this locality in the radial direction, and here you can see we can get it in this rather kind of simple setting.
I mean, one thing, a little counterintuitive.
Yeah.
Because you wanted to say that there's too much stuff in the bulk.
Yeah.
And now for each point in the bulk, or somehow you need 3 pieces on the boundary.
Yeah, right, exactly. So that's right. So let me I'm about to comment on that. So the first comment is that this is not a violation of the time slice axiom, which I talked about yesterday. So the time slice axiom, which certainly is true for the 3Q-trit model, says that an operator on the full Hilbert space, which commutes with all of the single site operators, has to be trivial. But I didn't show that it commuted on the whole Hilbert space. It only commuted on this code subspace. Okay, so that's why it's not a mathematical contradiction. But then you can say, all right, and this is basically what Eliezer is saying, is, in the beginning of the lecture yesterday, the very first thing I said is that AdS CFT is an isomorphism of Hilbert spaces. So I said every boundary state has a bulk interpretation and vice versa, right? So then you can say to me, okay, I mean, come on, Harlow, like you said that, but now you're giving me an interpretation of these 3 states, but what about all the other states, right? Don't those, what's the bulk interpretation of those? Show me that. Okay, so that's true. I do have to answer that. So here's the claim. The claim is that in the other states, the orthogonal complement of the code subspace, the picture you should have in the bulk is that now there's a black hole sitting here in those states. This point is gone, and the sort of the 24 dimensionality of the orthogonal complement is the microstates of this black hole. And so then it would have been a mistake to ask for this operator to be there and commuting with all the boundary operators because it's not there in this picture. Now, in this model, I can say that, and you can sort of, you can decide whether you believe it or not, right? I mean, it's not really clear. At least it's a thing I could say. We'll see, hopefully, throughout the rest of this lecture that this is kind of correct, so that we'll argue in more general examples. You can see that it's really sort of right to interpret this as the black hole. So somehow that's why. Yeah.
Sorry, O-twiddle does commute with all the local operators on the boundary here.
No, because so I've only defined O tilde, how it acts within the code subspace. I have to define it on the rest of the Hilbert space. Okay, but the claim is no matter how I do that, if I remove these states and I just look at this operator, I won't get 0.
Okay, commute within those states.
Within those states, yeah, that's right. But now it's not a contradiction because the code subspace doesn't have the tensor product structure. it's only the full Hilbert space that has that structure. And that's the whole point of quantum error correction, is understanding the interplay where you have a larger Hilbert space that tensor factorizes, but then you pick a subspace that doesn't respect that tensor factorization. And then you want to understand the interplay between the two.
Are those points outside the horizon?
Yeah, so in this model there aren't. So yeah, the bulk is pretty trivial here. So there's just this one point, and then once it's gone, it's gone. So the models I'll talk about later have points outside the horizon. Yeah. Yeah.
X3 is meant to act on the entire Hilbert space?
Yeah. X3 is some operator that's localized here. So whenever I talk about an operator that's localized here, I have to be talking about the whole Hilbert space, because then I'm using the tensor factorization. So this X3 is an operator that does not respect the code subspace. Well, 3 and in fact many more, because I've only defined it on a three-dimensional subspace, so I have a lot of freedom for what it does on the orthogonal complement. And so these different O12, O13, O23 will do different things on the orthogonal complement, but I don't care. Yeah.
Can you discuss symmetries in these holographic movements?
Yeah, but that's the last lecture, so I'm not going to talk about it now. Okay, so that's kind of where I wanted to close yesterday, with this simple model, so that hopefully at least this convinces you that quantum error correction is possible. And now today what I'm going to do for most of the lecture is present two sort of general theorems about quantum error correction, because this is just some model, right? So you have no idea whether what happened here is generic or it's just some funny thing, like Zohar's U1 2 and U1 minus 2 that only happens if it's 2, right? So then it's not so interesting. So here I want to say that it's a general the structure is representative of what happens in quantum error correcting codes. Okay. So I think actually I'll erase and start over. Because now I prove some theorems, so it'll take space. Yeah.
O can be represented on 1 and 2, and that's why it commutes. But what if you represent it on 3?
So then it doesn't manifestly commute. But if I can show you that this is 0, then it's 0. However, as long as I have one way of showing you that it's 0, as long as mathematics is consistent, then it's 0. Yeah. Yeah, so I'll give an example with more states later in the lecture. Yeah. This is just one example. So obviously, we need to say some things more general than just this example. Okay, all right, so now I'll talk about general properties of quantum error correcting codes. So the first thing I'll do is I'll give kind of a structure theorem. And I'll even prove the theorem just because I want you to see some of what the techniques are that people use in thinking about quantum error correcting codes. So yesterday was fluffy, today we're rigorous. So let H code be a subset of a Hilbert space that tensor factorizes into HR and HR bar. So you can think about this as like, this is the subregion of the boundary that you have access to, and this is the subregion that you don't, if you want to think about it that way. But here we're just doing linear algebra. Okay, so then the claim is that the following are equivalent. Okay, and there's going to be 4 things. Okay, so the first is for all O tilde on H code. So that means operators where both the operator and its Hermitian conjugate preserve the code subspace. Then there exists an OR on HR such that for all psi tilde in H code, so I can kind of give a little more space there, we have that OR psi tilde equals O tilde psi tilde, and OR dagger psi tilde equals O tilde dagger psi tilde. Okay. So to be clear, the proof is not saying that this is true. It's saying if this is true, then there are three other things that are also true and vice versa. Okay. So, but this was true in the example we just discussed. So this is saying that the logical operators on the code subspace can be represented just on this tensor factor. Okay. Okay, so that's condition number one. Condition number two is that for all operators x r bar on h r bar, we have that. So P will be the projector onto the code subspace. Okay, so this is a subspace, and I can define an operator P which projects onto the subspace. So the claim is that P x r bar P is proportional to P. Okay, so that's the second condition. So if you like, for any sort of error, any operator acting on the region you don't have access to, if you project it onto the code subspace, you get something that's just the identity on the code subspace. 3. So I can define a state phi, which is, so there's some normalization factor. So I introduce an auxiliary Hilbert space whose dimensionality is equal to the dimensionality of the code subspace, which I'll call S. And then I prepare a maximally entangled state of that auxiliary system with the code subspace. Okay, so that's something I can do. I have some subspace of this Hilbert space, and I can always introduce some auxiliary system and then just prepare a maximally entangled state between the auxiliary system and the code subspace, and I can take the dimensionality of the auxiliary system to be the same as the dimensionality of the code subspace. So this absolute value of S is the dimensionality of the code subspace. Okay.
This factorization R bar is any kind of factorization, or is there some map from R HR to HR bar?
No, it's just this tensor factorization. Yeah. At some point, someone might complain that this tensor factorization isn't true in quantum field theory, but I'm going to not respond to that complaint. Okay. All right. So this is a state, but to give a condition, I have to say something about this state. So the condition is that that if I look at the reduced density matrix on S and R bar of this state, it tensor factorizes into rho S of phi tensor rho R bar of phi. So it's saying that in this state, there's no correlation between S and R bar. If you look at the reduced state on S and R bar, you get a tensor product state. And then the final condition, which is a little bit annoying to write, is that the dimensionality of the code subspace is less than or equal to R. We can decompose HR in the following kind of funny way. With R1 equal to S, and R3 less than to S, less than the absolute value of S. And there exists a unitary operator, UR, with support just on R, and a state, chi, on R2 times R bar, such that, and I'll explain the motivation for this in a sec, but first I have to write it, such that if we look at a basis of the code subspace, then it has exactly the structure that we just wrote down for the 3-qubit code. So we have I on R1 times chi on R2 R bar with a unitary acting on R. Okay. So sorry, that's a... You can, for the most part, just ignore these statements about the dimensionalities. They're just there to make sure that I can fit the code state here into R. Okay, because if R was too small, then I couldn't even fit the message there, even if I wanted to. Okay, so that's all that this is saying. And this decomposition is something I can always do by long division. So I just, since S is less than R, I can divide R by S with remainder. And so the dimensionality of this R3 is the remainder. Okay, so that's some, elementary school arithmetic. Yeah.
Is the condition for any decomposition of HR this way? There exists unitary.
Yeah, that's right. Because I can since I have an arbitrary unitary on R here, there's no uniqueness in this. I can do it however I want. Yeah, that's right. Okay, so basically what this one is saying is that the structure of a general code is going to be the same as what we had for the 3-qubit code. You'll have this chi state here kind of hanging out, and then you'll have the unencoded message here, and then you'll encode with a unitary on R. So I can draw a picture of that just to make it a little bit more intuitive. So there are these things called quantum circuit diagrams, which hopefully are self-explanatory. So the idea is I feed in the state psi, and then I feed in the state chi, and then I act with the unitary on R. And so here's R, and here's R bar coming out. And this circuit gives you psi tilde. Okay. So in these diagrams, the subsystems are lines going up. So I feed in psi into this subset of R. I feed in chi into the rest of R and R bar. And then I act with the unitary UR up here. And this prepares the encoded state. Okay. Now let me just say a little bit about how to prove this, because I think it's good to see how to think about this kind of thing. So the way, as with any of these things, the way you do the proof is you show that 1 implies 2, implies 3, implies 4, implies 1. Okay. So let's first do that 1 implies 2. Okay, so we say that we assume that for any logical operator on H code, we can represent it just on R. Okay, so then we can say by contradiction. So say there exists an XR bar such that P XR bar P is not proportional to P. Okay. So that means that the projection onto the code subspace of this XR will be some non-trivial operator on the code subspace. Now, by Schur's lemma, if I have an operator which is non-trivial on the code subspace, then there will be some other operator on the code subspace that doesn't commute with it, right? That's always true. So let's call that operator O tilde. So then there will exist some, so this implies there exists O tilde such that, and also psi tilde, such that the commutator of O tilde with P X R bar P psi tilde, which is equal to psi tilde, the commutator of O tilde X R bar, because this P is always acting on a state in the code subspace, so I can ignore it. It implies this is not equal to 0. Okay, for some O tilde and for some psi tilde. But clearly this is in contradiction with 1, because I can just represent O tilde on R, and then these two are commuting. So I don't blame him, it's yeah. So this would contradict 1. So it must be that for any such X bar, this is proportional to the identity on the code subspace. Okay. Yeah. So O tilde is an operator that preserves the code subspace. So when I act with O tilde on the left on psi tilde, I get a code state. So I can still I can get rid of the P in that direction also. Yeah, that's right. Okay. So that's 1 implies 2. Not too bad. Now let's do 2 implies 3. Okay, so the idea here is that we're going to look, so now we want to show that in this state phi, if we look at the reduced state on S and R bar, the state is a tensor product. So one way to show that a state is a tensor product is to show that all the correlation functions factorize. So if I can show that in the state phi, the connected correlation function of any operator on S with an operator on R bar is 0, then that's the same as showing that the states tensor factorize. You can go and prove that for yourself as a homework problem, but hopefully it's fairly obvious.
What is the correlation function? There is no space or time here, just linear algebra.
Yeah, no, I just mean the expectation value, the product of the expectation value of the product of the operators minus the product of the expectation value of the operators. Yeah, that's all I mean. Yeah, I'll write it here. So what I want to do is I want to compute phi OS x r bar phi for OS being an arbitrary operator on this reference system, and x r bar being an arbitrary operator on R bar. And I want to show that this is equal to the product of the expectation value of OS with the expectation value of R bar. Okay, that's the same as showing that it's a product state, if I can show that for all OS and XR bar. Okay, so let's do that. Well, the first thing I can do is I can insert these, I can put a P here and a P there, okay, because the P now commutes with this because it's acting on a different tensor factor. And then acting on phi, the P is trivial. So this is the same as phi OS P x R bar P phi, okay? Now we're assuming condition 2. So we're assuming that P x R bar P is proportional to just the projector onto the code subspace. And so that means that this thing is proportional to it's something that commutes with, how shall I say this? It's something that is proportional to the identity in this correlation function. So it means that this is going to factorize. So I can write this as phi OS phi phi P x R bar P phi. So let me say that maybe in a slightly better way. So I can insert a complete set of states here in where phi is one of the basis elements, and then all the other ones will contribute 0. So then I just get this. Okay, but now here again I can get rid of the p's because they're just acting on phi, right? So, and then once I get rid of the p's, then it's exactly saying that this correlation function is the product of the two operators. Okay, and so that shows that it's a product state. All right. Let me see. Now I have a problem with what to erase. I actually should probably erase what I just did, since I should leave the statement of the theorem on the board. So I'll start at the top. So. Okay. Now the 3 implies 4 is kind of the hardest step. Because I have to use some properties of pure states in quantum mechanics. So in particular, I need to use 2 properties of pure states, which I'll just tell you. Okay? So say I have a Hilbert space, which is a tensor product, HA times HB. Okay? The claim is that if you look at the reduced density matrix of any pure state on A, and the reduced density matrix of any pure state of the same pure state on B, those density matrices have the same non-zero eigenvalues. So that follows from something called the Schmidt decomposition. So if you don't know what the Schmidt decomposition is, go learn it, because it's a kind of essential thing in quantum mechanics. Basically, it says that every pure state on a bipartite system, in some basis, has the form, Ci, I on A and B. So in appropriate bases at A and B, every pure state looks like that. The basis obviously can depend on the state. Okay. And so since this is true, it means that the non-zero eigenvalues have to be equal because they're just coming from these C's. Okay, so that's one thing I need to use. The other thing I need to use, which also follows from the Schmidt decomposition, is if I have, so if I have 2 states, so if I have psi and phi, which are both elements of HA, tensor HB, and moreover that the reduced density matrix on A is the same for both phi and psi, then it follows that psi is equal to some unitary on B times phi. Okay, and that again follows from the Schmidt decomposition. So two purifications of the same state onto the same system could differ only by a unitary on the system that you're purifying onto. Okay, so those are things you should all understand. So if you don't, go work them out. All right, now using those two things, I can show that 3 implies 4. So the first comment is that, so now we're assuming 3. So since phi, so phi is a purification of rho r bar s. Okay, clearly, right? I mean, if because I got rho r bar s by taking the partial trace. So that means that we must have that the rank of R is greater than or equal to the rank of rho r bar s.
I just wanted to make more comments
Yeah.
on the Schmidt decomposition.
Yeah.
You said it was slightly imprecise because there could be additional zero eigenvalues.
Yeah, so I said the non-zero eigenvalues are equal.
The
That's what I
non-zero
said.
eigenvalues.
The non-zero eigenvalues are equal. That's what I said. Yeah. Okay. So this just follows from what I just said. So whatever the rank of this is. So on R, yeah. I mean, this must be true because if this is not true, then we can't fit the purification of this into R. Okay. There just aren't enough states to fit into the Schmidt decomposition. Okay. Now, this is a product state. That's assumption 3. Okay. So that means that the rank of this is just the product of the rank of rho r bar with the rank of rho s. Okay. But rho s is just the identity, right? If you look at this. Okay. So so this is just equal to the dimensionality of the code subspace times the rank of rho r bar. Okay? And in particular, this implies that S, the dimensionality of S is less than or equal to the dimensionality of R. Okay, and that was one of the things that I wrote here. Okay. Now, moreover, by long division, which I already alluded to here, we can always make a decomposition where R3 is less than S, and R1 is equal to S, because I just divide the dimensionality of R by S with remainder. Okay. So I will have that decomposition. Okay. So that means that so now I can massage this equation a little bit. So this says that the rank of rho r bar has to be less than or equal to the rank of R divided by S, but via this long division argument, that's the rank of R2 times the rank of S plus the rank of R3 divided by the rank of S. Okay, so that's equal to the dimensionality of R2 plus R3 over S. And so in particular, that implies that the rank of rho r bar is less than or equal to R2, dimensionality of R2. Okay, and what this means is that I can purify r bar onto R2. So that means that so this means that I can write a state phi hat, which is equal to 1 over square root of S sum on I s I r1 chi r2 r bar. So to be clear, the existence of the chi follows from this. So because this is true, it says that there is some pure state whose reduced density matrix on r bar is rho r bar. And so that state I'm just calling chi and putting here. And then we can check that this state has the same density matrix on S times r bar as phi. Okay? So if we trace out R2 and R1, then we get back exactly row R bar tensor the identity on S. And finally, I can invoke the Schmidt decomposition again to say that since this state and this state phi are the same on R bar and S, then they must differ by a unitary transformation on R. And that is this statement that I wrote here. See? So from the Schmidt decomposition, we get this conclusion. Okay, so that's the hardest one. Sorry about that. But it's good to learn about the Schmidt decomposition.
Something here is kind of a little confused.
Yeah.
So you made in one, there was this condition that O dagger
Yeah.
acts on the code subspace.
Yeah.
But so for that, you need some kind of canonical identification of the dual space and the space. And this canonical identification is not invariant under changes of variables.
Well, sorry, but I mean, the Hilbert space inner product is fixed. I'm allowed to use that, right? So
Right, but then you're only allowed to use unitary changes, unitary transformations, not general linear transformations.
Yeah, that's true. But I mean,
So I wonder if to get the Schmidt decomposition, you can still do that. Because
yeah, you still can. This is a unity. It's a unitary change of basis to get to the Schmidt decomposition. That's correct. Yes. Yeah. Okay. Okay. So that's 3 implies 4. That's the hard one. So 4 implies 1 is actually obvious. So I'll just say it. So if we're given 4, so we have this UR, then we can just do the same thing that we did in the 3Q trit code. So we can act with UR dagger, and then we can act with whatever logical operator we want, and then we can act again with UR. Okay, and that gives an operator with support only on R. Like if you just look here, right? I act with UR dagger, then I act here with whatever operator I want, but this R1 is part of R, and then I just re-encode with UR dagger. Okay, so if I have this structure of the code subspace, then I clearly have this. Okay, and that concludes the proof of the theorem. Okay, so hopefully educational. Okay, so in kind of so probably I think the moral of this, since maybe okay these conditions, okay whatever, the moral is to remember this picture. Okay, it says that for any error correcting code with this property that all the operators on the code subspace you can represent them here, or any state on the code subspace you can recover. It has to come from this kind of circuit diagram where you feed in the unencoded state, you feed in some chi, and then you use a U on R to encode. Okay. So in other words, it's saying the structure of the 3Q trit code is totally generic, at least for this kind of thing. Okay, so that's one of the 2 general results I wanted to tell you about quantum error correction. Yeah.
Question for practical purposes. Since
Yeah.
this code subspace is a tiny, tiny subspace of the full space,
Yeah.
I guess generically it's exponentially bigger in the full space.
Yeah.
And so how practical is it to even hope that you can arrange states in that subspace?
Oh, you mean like in practice? Like you mean if you're trying to build a quantum computer?
Yeah, I mean a generic state would not be in the code subspace. So how do you make sure that your states are in the code subspace to begin with?
Well, that's the general problem of how do you build a quantum computer. So if you have control over the quantum state, you can do it.
Yeah, but
So what can I say? I mean, it's hard to build a quantum computer. I agree.
well,
But I mean, let me add though that it's not that hard because quantum mechanics is linear. So the errors in the Hilbert space don't accumulate. If 2 states differ by a little bit and then you evolve, they continue to differ by a little bit. And so that's the only reason why there's any hope of building a quantum computer. Yeah.
So there's no, the discreteness was very important. The fact that you have the finite dimension.
Yeah, well, certainly, yeah, in the proof I gave it, that's correct. Yeah. And most of the work in this subject has been along the lines of within finite dimensional Hilbert spaces. There has been some work. So if you want to do it in infinite dimensional Hilbert space, you have to lift all this into von Neumann algebras. You don't want to talk about these ranks and so on and states and this. You don't have the tensor product. Okay, I'll say one thing about not having the tensor product. So of course in quantum field theory you don't have this tensor product, but what you do have is you have the algebra operators in one region and the algebra of operators in its complement. And so there's an algebraic reformulation of all of this, and I'll actually say a little bit about it tomorrow. There's an analogous theorem. So I proved actually a theorem analogous to this one in terms of von Neumann algebras, but still acting on finite dimensional Hilbert spaces. And then recently there was a paper by some students at Harvard, Monica Kang and David Kokelmeyer, I think, who extended my theorem to von Neumann algebras on arbitrary Hilbert spaces, or at least some subpiece of my theorem. But yeah, I'm not sure exactly how it works. Okay, so yeah, sorry, another question? Yeah, Monica's proof. Yeah, it does. Yeah, I think so, yeah. Yeah, I was kind of too scared to try and do that myself, but I guess these people are more mathematical, so they were...
Don't we need to supplement this whole machinery with some control over what happens if you deviate a little bit from the code subspace?
Yes, that's correct. So there's also a whole version of this where you put in epsilons and you say, if you put in error bars in each of these, then you can relate the error bars.
And how does that affect the computation? Like if you want to factorize the number, I mean, that would end up in being what, some probability of error?
Yeah, that's right. So that's right. But so the thing is, you know, as long as if you have an error probability which is small but order 1, it's actually fine because you just do the computation 10 times and now it's better. So you know, yeah. I mean, so there's a whole. I mean, this is only the beginning of quantum error correction, right? I mean, there's a whole theory of trying to do fault-tolerant quantum computation, and this is like one part of that. You know, so when you're really doing the whole story, you know, you assume every single thing you do, every unitary you do, it could have an error. Every state you didn't prepare it quite right, and then you kind of trace how the errors go through, and you can basically show that as long as the fundamental operations can be done with error probabilities that are sufficiently small but order 1, like say maybe 10 to minus 4 is the kind of thing people talk about, then you can make the whole shebang work. There's actually kind of a phase transition. So for error probabilities above that, the errors accumulate and you're screwed, and then for error probabilities below that, you can do arbitrarily long computations and have them work. So you kind of have to make sure you can catch the errors as fast as they accumulate, and as long as you can do that, you're okay. All right, so this is the kind of general structure. The other theorem I wanted to talk about puts some bounds, right, on things like, so you might think, like, how big can the code subspace be if you want to protect such and such amount of information? So I'm going to now prove an inequality about that. That kind of gives you some sense of how well this can work. Clearly, there's got to be some bound. You can't, you know, protect arbitrarily things as much as you want. And then later in the talk, I'll try to relate that bound to things involving how much stuff you can put in the bulk before you form a black hole. Okay, so the next thing I'm going to talk about is called the quantum singleton bound. So it's a bound, you know, basically sort of giving an upper bound on the dimensionality of the code subspace in a special family of codes. It's codes where the size of the erasure. So the question of which. So say we have n. I'll call them qubits. They could be qubits, but let's just call them qubits. So say you have n qubits, and you have some code subspace, and then you want to know how many of the physical qubits can you lose and still recover the message. And so what I'm going to assume is that there's a symmetry, so that the question of whether or not the loss of any particular set of qubits is recoverable is determined only by the number of the qubits. It doesn't that you lost. It doesn't matter which ones you lost. So you know that won't be true in general, right? And actually in holography, depending how you do things, it won't be true. But for example, in the 3 qubit code, it was true, right? So we could recover from the loss of any 1, but not from the loss of any 2. Okay, and the sort of the most standard error correcting codes that people talk about have this property. And actually, if you're doing a quantum computer, it's kind of what you want because you know any of your qubits can be screwed up. You know, you probably shouldn't preferentially treat any of them. So that's going to be the assumption. There's a symmetry. So in particular, that means so I have n qubits.
Symmetry is just being a permutation.
Yeah, permutation symmetry. Yeah. So there will be a number m, which is so m will be the smallest number from which we can extract the logical information. So, and here the assumption is that if I have m of them, I can get it, regardless of which m that I have. Okay. Now, there's an obvious bound on m. So, it's clear that m has to be greater than n over 2. And the reason is because if m were smaller than n over 2, then I could fit 2 of the m's into the system. And then that would violate cloning, because I could send in the message, and I could take these m and I could take those m, and that would give me 2 copies of the state. Okay, so the no cloning theorem says I've got to at least have this. All right. Now, because I have that, it means I can split up. So say here are my qubits. I can split it up into a collection A of n minus m qubits.
That's essentially the page bound, right? The same idea as the page.
Yeah, this is kind of like the page bound, but you're going to see in a sec that the full statement is going to be even more like the page bound. That's right. Yeah. That's kind of the intuition for the page bound. So I can split it up into a set A of n minus m qubits, another set of n minus m qubits, where now since m is greater than n over 2, n minus m is less than n over 2, so I can fit in 2 of these. And then the remainder will be some collection C of the remaining qubits. Now, because of the theorem that we just discussed, so I can prepare this state phi, where I have the reference system, and then I have the encoded state on ABC. Okay, and then we just learned that phi. So since I can recover the information from both A and B, it must. Sorry. No, I can't. Sorry, I can't recover the information from A and B. So it must be that the state on A and S factorizes, and also the state on B and S factorizes. So that was condition 3 in the theorem. So we're assuming that since we're recoverable, it means that rho AS of phi is equal to rho A of phi tensor rho S of phi, and the same for B.
So now you're assuming that it's recoverable.
Yeah. So now I'm assuming because I said that here. I said with any m you can recover. Okay. Yeah, for any set of the m is a fixed number. M is the number such that if I have m of the qubits, I can recover, or more. Clearly, if I have more than m, I can also recover, because I can just ignore some of them.
That would only lead to a necessary condition on m. But you're assuming that such an m exists, and then you can obtain a bound on it.
Yeah. But I'm going to give an inequality which holds if you can recover with m of the qubits. That's correct. Yeah. That's right. So in particular, so I can recover on B and C, or I can recover on A and C. Okay, and then the theorem tells me that rho AS has to tensor factorize, and also rho BS has to tensor factorize. Okay. So that implies that if I look at the von Neumann entropy of the state phi on A and S, it's equal to SA plus K log 2. So here, I guess the log 2 is just because I defined the von Neumann entropy log E, where maybe I should have done it log 2. And similarly, SBS is equal to SB plus K log 2. Okay. So that's just the property of von Neumann entropy, is it's additive on a product state. Okay. Now, okay, here's another homework problem. So von Neumann entropy has this nice property that SA plus SB minus SAB is greater than or equal to 0. Okay, that's true for any state. That's the subadditivity of von Neumann entropy. So in particular, that this tells me that SAC is less than or equal to SA plus SC, and BC is less than or equal to SB plus SC. Okay. So now I'm going to combine a bunch of things that we already said. So first of all, I have that K log of 2 by this is equal to SAS minus SA. Okay, that's what this equation says. And moreover, another property of von Neumann entropy, which follows from what we said about the Schmidt decomposition, is that if you have a pure state, then the von Neumann entropy of one system is equal to the von Neumann entropy of the complement system. Okay, so that means that this is equal to SBC minus SA. Okay, and then by subadditivity, you see now I have SBC here. So this is less than or equal to SB plus SC minus SA. I can do the same thing for the other set of things. So I can do SBS minus SB, which is equal to SAC minus SB, which by subadditivity is less than or equal to SA plus SC minus SB. Okay? Now, look at these two things. So it says that, both of these have SC, and then we have plus SB minus SA, and we have minus SB minus SA. And both of those have to be upper bounded by K log 2. So that's only possible if K log D is less than or equal to SC by itself. Because, log 2 is less than or equal to SC by itself, right? Because here we added something and here we subtracted something. So if this weren't true, then clearly one of them would violate the inequality. Yeah, you can just add the two inequalities. Right, exactly. That's right. And so, moreover, SC has to be less than or equal to so we can add how many qubits are in SC, right? It's n minus 2 times n minus m. Okay, so that's whatever m minus n. Okay, so this has to be less than or equal to. I did something wrong. There's a 2m, right? Is that okay? Yeah. That's right. So this has to be less than or equal to 2m minus 2 log d, or log 2. So then I can ignore the logs, and what I get, so this is the quantum singleton bound. I get that m has to be greater than or equal to n plus k over 2. Oh, sorry, yeah. Jet lag. Okay, so this is the quantum singleton bound. Okay, so now let's make a few comments about it. So it looks, it looks like this one, but actually it's a strengthening, you see, because now I have k here, and this is the thing that's really like page. So it says that to recover.
Maybe explain also what page is for some.
Oh well, page is this actually. It says that if you want to recover k bits from a black hole, you need k more than n over 2 of the bits to do it. Yeah. So it kind of makes sense. Like if you want to protect a bigger message within a fixed number of qubits, then the number that you need to recover is going to be bigger, right? So the errors you can correct are going to be smaller. You can also say it in the other way. So if you want to, if you fix k and then you want to be protected against bigger errors, then you have to increase n. So it also kind of makes sense. Also, you kind of more redundancy helps protect you against larger errors. If you want a bigger message, you're less redundant. It's however which way you want to say it. Okay. All right. So that's the quantum singleton bound. Good. So let's check for the 3-qubit code.
Well, then it's saturated.
Yeah. So but then you can saturate it.
Well, no, I meant in general for general and.
Oh, you mean is there always an example? Yeah. No. Yeah. But.
Just a necessary condition. So
Yeah, there's just a necessary condition. Yeah, so let me comment on that now, actually. So first for the 3-qubit code, well, I did the proof for qubits, But had I done qubits, just the log 2s would have been log 3s, and nothing would have changed. So let's check. So for the 3 qubit code, right, what's n? Oh, what? K is the number of qubits in the code subspace. I'm sorry, I didn't define that. Very sorry. Guilty as charged. K logical qubits. And there are n physical qubits. Yeah, I should have said that. I apologize. Yeah. Yeah. Okay. Where did K first appear? So where am I first guilty of that? Just in the end. Okay. No. It appeared here. It appeared here. Here. Yeah. It appeared.
K is the dimension of this.
Yeah, it's also the dimension.
Well, 2 to the K is the dimension. Yeah, 2 to the K is the dimension. That's right. Yeah, it was the dimension of SS. Right. That's where it came from. So it's the dimensionality of the reference system is 2 to the K, and that's equal to the dimensionality of the code subspace. Sorry. Yeah. Okay. So let's check for the 3 qubit code. So what's n? See who's paying attention. Only students are allowed to answer. What's n? 3. Yeah. It's the number of physical degrees of freedom. Okay. What's K? Right. And how many do we need to access the message? Right. Okay, so now let's check. So this is a challenge, but let me try. So this is 3 plus 1 is 4. And you divide by 2, it's 2. So that's good. But you're right in the edge, right? Like, you just barely make it. Now, you can ask, generically, how close can you get to saturating this inequality? So in fact, you can show that, so if you take n to be large, and then you choose just a random subspace of dimensionality 2 to the k, you can show that these correctability conditions I was talking about hold approximately up to errors that go basically like what you want in this inequality. So something like 2 to the, 2m minus n minus k. So a generic subspace will, a generic subspace whose dimensionality is chosen to be on the right side of this equality, the code will in fact be correctable. So I think in my paper with Almeri and Dong, we gave the proof of that, or maybe just quoted it. If you know about how to do random matrices, it's easy proof. Basically what you do is you show that the correlations functions factorize up to errors of order this size, and then actually, also in the paper, we give some of the approximate versions of these conditions and show how they're related in that paper. Okay, so this is sort of the words I like to say about this is that it's sort of necessary and typically sufficient. But of course, you can be unlucky. For example, you could just put the code. You could just put the message in the first qubit, and it doesn't matter how many more you add; it's not going to help. Okay. All right, so that was all I wanted to say about the sort of general properties of quantum error correcting code. So now let's try to apply what we learned to holography. So I have a half hour more. That's the.
But that's
In 1 minute, you have half an hour.
Yeah.
But practically, that means that you have to make sure that the environment would not corrupt more than 50%.
Yes.
Otherwise, you're completely dead.
Yeah. But right. And probably even soon, well before that. Yeah, depending what you're trying to do. Yes. Yeah, and that's just, that's true in any code, right? Also with sending the message to the Voyager, right? If half the bits get corrupted, no code is going to save you. Yeah. Unless you know exactly which half and you're careful to avoid that one in sending the message.
No, practically there is no such bound. Practically you can send an exact clone like 100 times and then you don't care for updates.
Yeah. No, but there is still some kind of bound because you can ask, because even if you send 100, if you lose 60, you're dead. So, yes.
Because you'll get 40 which are exactly the same.
No, sorry. Well, it depends on what your error model is, I guess. Yeah.
It
Depends on the error model. That's right. If it's just taking things away, no, that's right. Then it's fine. Yeah.
Completely malicious and random. Classically, you can just send 100 copies and you're good.
No. If the environment is completely malicious, it won't just take away qubits. It'll flip them, and then you right. So say the probability is that it instead of stealing the qubits, it just flips them and sends them along. Now if it flips 60, you're dead, you know?
That's right.
Yeah. Even classically, you can't recover from that. Yeah. Okay. So now what I'm going to do is use these results to kind of interpret the AdS CFT as a quantum error correcting code. Okay. So the first thing I want to do the first thing I need to do is I need to pick a code subspace. So far I've been a little bit vague about what code subspace in AdS CFT I want to talk about. And in fact, there's kind of a reason for that, which is that there's no canonical choice of code subspace. So the code subspace is something that you should think of as being like a choice of renormalization scheme. You pick it based on the physics you're interested in, and depending on what you pick, the error correcting properties will be different. So let me start by picking an exceptionally simple one. So the simple one is we start with the vacuum, and then I pick some small region right in the center of AdS. And then I say that within this region, you're allowed to act with k operators, but k bulk operators and not more, and smeared and not right on top of each other and so on. So we can have phi, phi dot, phi squared, or whatever, but some order k of these operators. Okay. So then the dimensionality of H code will be exponential in k with some coefficient that I'll call alpha. Well, as I said, it's a choice. If I'm interested in what's going on over here, then clearly this is a stupid code subspace to consider. Okay, I'm just picking a code subspace and we're going to study its properties. This won't be the only code subspace I ever consider, but it's a nice one to see how things work. What do you mean smaller bit? I didn't tell you what is k. K could be 2. Okay. So now the question I'm going to ask is, if I'm given a ball-shaped region in the boundary of radius r, what is the smallest radius r such that I can recover this information? Okay? And because that's why I put it in the center, is that then it'll just depend on the radius and it won't depend on where the balls are. So that's because I wanted to get into a situation like with the quantum singleton bound. Okay? Now it's not quite literally the same as the situation of the quantum singleton bound, because I could put some of the region here and some of the region there. But actually we'll see that exactly the same argument works if I restrict the regions that are contiguous. And in fact, I'll restrict to ball-shaped regions. Okay, and then it should be true that there's some r min, where if r is equal or bigger than r min, then I can recover what's going on in the center. Okay, now for any region, now there's a bit of a notational class. Okay, let me say for any region A, I can put an upper bound on the entropy in the region A. And you might at first say, you're right, so basically now I'm going to have to kind of tell you in AdS CFT what are this n and m, right? Now, naively, of course, if I pick a subregion A in quantum field theory, the von Neumann entropy could be infinite, right? In fact, is infinite, right? But that's because of the short distance divergences at the edges of the region, which have to do with very high energy physics in the CFT. And so if I'm only interested in these states which are near the vacuum, I can integrate out almost all of the degrees of freedom. I can basically, choose to set the lattice spacing, maybe, 1,000 lattice sites on the sphere, and I can integrate everything else out above that, okay? And so in that regulated theory, I'll have a bound, which is that the von Neumann entropy in the region A will be less than or equal to some coefficient that I'll call gamma times the number of degrees of freedom at each point, which I'll call n to the sharp, times the volume of the region A. Okay? That just, in any lattice theory, that'll be true. You have the number of sites per lattice spacing, you have the volume, and then some order 1 coefficient. Because remember here, the lattice spacing I'm taking to be morally of order the size of the sphere. So now by using I can do exactly the same argument I did for the quantum singleton bound. So I can I can have 2 regions, A and B, which are sort of as large as they could be without being able to recover the information. And then I can call their complement C. And then the argument that we just did for the quantum singleton bound will tell us that the logarithm of the dimensionality of H code has to be less than or equal to the von Neumann entropy in the region C. So that's what we just showed. And then this we can bound by gamma times n sharp times the volume of C.
Wait, this part, the first inequality is trivial, no? It's just like you're able to fit the code into the...
No, it's a little bit more. I'm sorry I just erased it. But because the SC is kind of the, remember there's 2 of these, right? That would be true if I just had the B. If I just had the A.
Talking about this inequality.
This one.
Yeah, if you want to recover the code.
No, you're not recovering it from C. You want it from BC.
Yeah. I'm recovering it from BC and AC, not from C.
Okay.
Yeah.
BC?
Yeah. Remember that was what I did before, right? I kind of, this is the maximal thing you can't recover from. So BC or AC is sort of the minimal thing you can recover from.
Recover from BC now.
Yeah, that's right. From BC or AC. And then I run the same argument with the entropy inequalities to conclude this, and then I use this lattice argument to conclude this. Okay. Now let's say that V min is the smallest volume of a ball that I need to recover the information. So what the singleton bound tells me, so remember well, I erased it, but it said that m had to be greater than n plus k over 2. Using these, it tells me that this volume needs to be greater than the volume of the sphere, the volume of the whole spatial boundary, plus alpha gamma inverse n to the minus sharp times k. Where here I've used that the dimensionality of the code subspace is e to the alpha k, and then I've just used this bound on the regions. Okay. So this is like the QFT version of the singleton bound. So now let's interpret what this equation tells us. So let's first consider the case where k is smallest, somebody suggested. So let's say, maybe we just act with, 20 fields or something in the center. That's it, small code subspace. Okay. Well, n is big, so then we can ignore this term. And then what this inequality is telling us is that our ball needs to be bigger than half of the volume. Okay. And that's actually correct, right? That's what the AdS Rindler reconstruction also told us. It told us that if we wanted to recover this region in the center, we needed a boundary region which was more than half of the points. Okay. So we've confirmed what we got by solving bulk wave equations by using the quantum singleton bound. Okay, so that's sort of a first consistency check of this proposal.
How would this change if your flirt sometime at Stanford with the hot holography would be correct?
Hot holography? What?
Namely have gravity on the boundary as well.
Oh, I have no idea. You're way ahead of me. I don't know. I don't know how to think about that. Then it's quantum gravity on the boundary theory, and then all my assumptions are wrong. So I don't know. Yeah, I have nothing used. Probably every equation is wrong then. So I'd have to start from the beginning. Let me do something less ambitious, and let me just start increasing k. So, well, for a while, of course, nothing happens. So, by the way, the sharp, if we're doing n equals 4, the sharp is 2. It's just because I don't want to commit to interpretation of n. In 2-0 theory, it would be 3, right? Whatever it is. So, as long as k is small compared to n to the sharp, then exactly the same thing goes through. Nothing changes. Okay.
If you don't know what a sharp is, because you're looking at a very tiny subset of the Hilbert space, it may not be n squared, for example, in n equals 4.
No, I think it is, right? Because there's no argument that I can ignore the matrices at low energy, right? There's an argument that I can ignore states with, high momentum on the sphere. Those are going to be high energy.
Yeah.
But within the matrices, I probably need all the matrices, even to talk about things right near the vacuum.
If you single trace operators. Like you need 20 single trace operators, and that's it now.
Yeah, but if you think...
There's no n squared.
No, but I don't. But even to talk about single, double trace operators and so on, I don't think I can integrate out. I can't integrate out a bunch of the matrix and make it smaller, right?
Also, probably know like how the entropy grows for low temperature. Like low temperatures, low energy probably doesn't grow like n squared.
No, it doesn't.
Yeah, that's if you know exactly what you're looking for.
Yeah, that's if you know exactly what you're looking for.
You just try to build it because it's directed in CFT, but that's not what
Yeah.
you do.
Yeah, I mean, somehow this subspace will be very sort of unnatural from the point of view of the matrices, right? Like, it'll be some weird thing in the matrix. So, it probably won't respect the matrix structure in any nice way, I guess is what I'm saying. So I probably need all the components. Okay, so then, right, so now we can start cranking up K, so making K bigger. And nothing happens until we get to K of order n sharp. But then you see right when we get K of order n sharp, now the code starts breaking down. And so things that we previously could have accessed, we no longer can access. But that's good, because in the bulk, that's exactly when, if we act with of order n squared things here, then we know that the generic state is going to be some black hole, which is sitting here, whose size is of order the AdS radius. And so then it's sort of correct. Like if we now try to draw these causal wedges, what you find is actually they recede away from the black hole because of gravitational back reaction. And so I claim this is support of this proposal that sort of the orthogonal complement of the code subspace has to do with black holes. Certainly at least in this example. Yeah. Of course, there are other things that aren't in the code space, just where I put particles over here, but that's just, I could put those. Then I wouldn't have this nice symmetry argument to isolate this physics. Yeah, certainly not from this code. So in a code where you can have this guy here that's commuting with everybody at the boundary, then you can't be talking about the microstates of the black hole. Yeah, I'll give an example that I'll maybe start today and not finish. We'll see how to kind of realize that more explicitly in a model. Yeah. Okay, so that's the first comment about the general properties of holographic codes. I want to make two other general comments, and then it'll be tensor network time, or it'll be we'll say a little bit, and then Sunday will be tensor network time. Okay, so the first comment is that by conformal symmetry, I can now take this whole story and I can move it around, right? Merde. Thank you. So, for example, I can, I could now instead, have the code subspace be built of excitations over here. And then what you see is that actually now the code is kind of crappy, because So for example, here I can have a very small erasure, where now I can't access this point anymore. Okay. So this point is not very well protected. Whereas this point is very well protected. You need more than half. You need to mess up more than half of the system to lose access to this point. Okay, and so my claim is that this is kind of a new interpretation of the radial direction in AdS CFT. So if you have some information and you want to know whether it's near the boundary or deep in the center, you ask how well protected is it from erasures. And, well, if it's near the boundary, it's not very well protected because there's a very small erasure that can delete it. And then as you move in, it gets better and better protected. And that's really that's like a monotonic function. That's like a precise thing. And in particular, I want to emphasize that's kind of, the thing people used to say, is that the radial direction is like scale or something. So that's some fluffy thing. It's not really an equation. This is equation. Okay.
So what is the equation?
What?
Yeah, what is the equation?
Yeah. It's this. Okay. So given the excitation, you ask, what is the smallest region in the boundary, where if I delete that region, then I can't know what's going on with that excitation. So that's a function.
Can't know it's a continuous thing.
No, there's a crossover, right? Like I have this thing here, and then I'm moving this, and then it goes from knowing to not knowing.
What does it know mean?
Yeah, but how do you measure?
There is an
knowing?
error. You have an error on the not know versus know.
Well, I can say it the other way. I mean, you don't have to actively have an error. I can say how big does it need to be for me to access it. These two questions are complementary. So I can say, so then it's like, what's the sort of what's the smallest region I need to access it? It's the same thing.
But what does it mean to access?
Approximate state after subprecision.
No, I defined what I meant by access. I mean the operator I can represent on the subregion of the CFT.
Is there a real formula?
Yeah. I mean, it's from the AdS Rindler. We can basically derive it. Yeah.
What does it look like?
What is the formula?
Well, I mean, maybe there's some log. I don't remember. I have to do it on the board, but there's clearly a formula. I mean, you just see where these geodesics go.
Yeah,
Yeah.
but there's a unique.
Yeah, there's an answer. Yeah.
Which is monotonic. That's
Yeah.
all.
So let me now comment. So I don't want to say that the old intuition is wrong. What I want to say is that this is kind of a sharpening of the old intuition, because basically, if you have something near the center, it's basically saying you only need very low wavelength degrees of freedom, a very long wavelength degrees of freedom in the CFT to describe what's going on here, because that's basically the argument I made here. You can integrate everything out at short distance scales, and it doesn't matter. You can still talk about recovering what's going on here.
Yeah.
But then as you move this point to the boundary, the information about this operator is contained in these smaller and smaller regions, which then obviously you need more and more short distance information in the CFT to describe.
Why is it not the same as RG?
Well, I'm just saying there's an equation here. I can...
Well, in RG you can ask how well can you approximate a state by only turning on oscillators with low momentum.
Yeah.
And that's also a well-defined equation. You can just compute the norm of the state that you can get in the fully.
Well, I don't know. That's not the equation people usually write,
It's a very
though. I
different
mean,
subspace than the
yeah.
subspace you would think of in final field theory.
Yeah.
This is weird subspace of just small number of particles.
Yeah.
It's
What?
exactly the same thing.
Yeah, that's another thing you can say.
Exactly the same
Yeah.
with subspace. This subspace is
Yeah.
the larger subspace. Exactly the same thing. And you ask how well can you approximate that subset by acting with low momentum oscillators.
Yeah, I mean, I agree it's related. We don't have to make normative statements. We can, this is a sort of one precise way of seeing this connection. I'm happy to say it that way if you prefer. Okay, so that was one comment.
Can you help me understand, aren't these isometries just like diffeomorphism? So is it something like gravitational addressing that makes this a non-trivial statement? The AdS isometry?
No. So I had to pick a conformal frame in the boundary to have it. I mean, I said the center. Okay, and as soon as I said the center, that means I picked a conformal frame in the boundary CFT. Okay, and that's what makes the center well defined. Yeah. Okay, so that was one comment. Now the other comment is that, so this code subspace was very convenient for doing the quantum singleton bound, but on the other hand it's kind of silly because, what if we want to know about the correlation function of this operator with that operator, which clearly we want to know about, right? So somehow we should probably also think about a code subspace where we have both this operator and that operator acting within the code subspace. Okay. And now, by definition, that's going to be a code where the protection isn't so good in the conventional sense because for this operator the protection won't be so good. And so to deal with that, there's a generalization of quantum error correction you can define, which does not quite fit into the theorem that I presented earlier, where you say that. Here's my picture. So you say that you have H code, which itself now tensor factorizes into H little r bar, sitting inside of a H big R bar. So let me draw the picture. So here's R. And then the idea is that rather than demanding that all the information in the code subspace is recoverable here, you only demand that the information on this subfactor is recoverable. So roughly speaking, little r is the bulk degrees of freedom here. Little r bar is the bulk degrees of freedom here. Here's big R and big R bar. And then you demand that everything here is recoverable there, and everything here is recoverable there. Okay, so that's a generalization of what we had before. What we had before was the case where HR bar was one-dimensional. Okay, and this is a more natural structure from the point of view of AdS CFT, right? Because now we can have degrees of freedom all over the place in the bulk. Okay, so usually when I talk about quantum error correction in AdS CFT, I'm doing this. I just did this so I could use the singleton bound. Okay, and so this, then let me say, so I won't inflict it upon you, but for this structure, there's an analogous theorem to the one that we did before. Okay, there's 4 things that if you think about it for 5 minutes, you can figure out what the obvious generalizations are. The arguments I gave generalize to prove the theorem. Let me just draw the circuit diagram picture. Okay, so that theorem tells you that for any code like with this property, the way the encoding is going to work is, again, there will be some state chi. There will be little r and little r bar that you feed in. And now there will be a unitary on r and also a unitary on r bar. Like that. Okay? So it's kind of the obvious thing. So chi is split between r and r bar. Little r goes into big R. Little r bar goes into big R and r bar, and then you've got unitaries that you act.
This would be harder to interpret using RG, because this would mix high momentum modes and low momentum modes.
Yeah, that's right. That's right. So yeah, this doesn't have so obvious an interpretation because you have both kinds of excitations happening at once. But I mean, somehow that's what you want if you really want to be doing sort of bulk particle physics or something. This is what you want.
Yeah, that would be like doing RG, but keeping some massive particle around.
Yeah, that's right.
People keep the proton in the chiral Lagrangian.
Yeah, that's right. It would be something like that. Yeah, yeah. Okay, so that's all I wanted to say about general properties of holographic code. So I mean, these kinds of things, right? This is the structure in actual AdS CFT, modulo the fact that the Hilbert spaces are finite dimensional, so you have to switch to algebras. Okay. Okay, that's kind of it for that. Now, the next thing I was going to do, which I'll probably just start because I don't have so much time. So now we have 2 examples of holographic error correction. We have n equals 4 super Yang-Mills and its cousins, and we have the 3Q-trit code. There's a lot of space in between those 2, right? N equals, the 3Q-trit code is sort of trivial, n equals 4 is very hard. It would be nice if we had some models that were sort of also solvable, but sort of more like n equals 4 than the 3Q-trit code. And indeed, there are models like that which are constructed using tensor networks. So I think what I'll do now is I'll just tell you what is tensor network, but I won't tell you the model, and then next time we'll start, I'll tell you the model. Okay?
What about something like ABJ?
Yeah, that's what I meant by cousins of n equals 4. Yeah. I also don't know how to solve that. Sorry. Probably just need these 2. Okay. So tensor networks. Okay, so the idea here is now we want to, so before we had 1 logical Q-trit and 3 physical Q-trits. Now we want to get to a situation where we have n physical, and I'm going to do qubits now, and k logical qubits. And then clearly, right, what we want to do is we want to take n and k to infinity, right? We want to have some family of codes. Yeah, that's all I need. I'm not going to give the example. I'm just going to say what is tensor network. Okay. So how can I do this? Well, clearly what I need to do, so we know what n physical qubits are. What I have to do is I have to tell you what's a 2 to the k dimensional subspace of the Hilbert space of n qubits, which I want to interpret as the code subspace, and then try and convince you it looks like bulk effective field theory. Okay? So the way I can do that, the sort of most pedestrian way, is to do what I did for the 3Q-trit code. I just give you the wave function of all the states in the code subspace. What more could you want? Okay, so what does that look like? So there will be some tilde states. So they're k logical qubits. So I have j1 through jk. Each I and j is 0 or 1. And then I encode, and then I give you its projection onto some tensor product basis in the physical Hilbert space. Okay. So the idea is that we can just view this wave function as some tensorial object where it has I indices and j indices, each of which is either 0 or 1. Okay, I can just encode the wave function like this. So to tell you what the code subspace is, I just have to tell you what this tensor is. And the idea is that I'm going to tell it to you by constructing it using a tensor network. So what is a tensor network? Well, the basic idea is you build a big tensor with a lot of indices out of a bunch of tensors with a small number of indices by contracting the indices in some geometric pattern. So let me just draw one example, and that'll basically be it for today. So in my example, there will be 3 tensors, and each of the tensors will have 4 indices. Okay, so here's the idea. So I have, so the lines connecting the dots represent index contractions, and the lines that are sort of sticking out by themselves represent the indices of the tensor that I construct. So in this example, I guess I'll construct a tensor which has 4 I indices and 3, or maybe 2, yeah, I guess 2 j indices, j1, j2. And so what this looks like, and so maybe I don't know, we can call this k1, k2, and k3. So then there'll be sums over k1, k2, and k3. And then each of these building blocks, let's call it t. And now let's see if I can get this right. So then I'll have something like I1. I'll assume there's permutation symmetry on the tensor indices, because otherwise I'll get horribly confused. K1, K3. And then here we have T, J1, I3 with K1, K2. And here we have K, I4, J2 with K2, K3. And this just defines my T, I1 to I4, J1, J2. Okay. So that's kind of a trivial example of a tensor network. So to really give you the tensor network, I have to give you 2 things. I have to give you a picture, and I have to tell you what these individual component tensors are. Okay? And I'll do both of those things first thing on Sunday. So let's stop. The T's are all the same tensor, yeah. Yeah, I mean, they don't have to be. I mean, you can make more general tensor networks where they're not. Yeah, I will choose to have them all be the same. Yeah. Okay, so any questions? First. Okay, sorry.